So, how would you go about building a URL shortener? It seems pretty simple on the surface, right? But what if it had to handle 100 billion clicks every single month? That's the absolutely massive challenge we're going to tear down today. This isn't your average weekend project. This is a masterclass in building for hyperscale.
All right, let's start with this number. Just look at it for a second. 38,500 requests per second. And get this, that's the average read traffic. When a link goes viral, this thing can spike to over 100,000 requests a second. So what kind of architecture can possibly keep up with that?
Well, this slide really puts it all into perspective, doesn't it? We're not just talking about throughput. We're talking about architecting for 100 billion reads a month, dealing with 60 terabytes of storage, and this is the kicker, keeping that response time under 10 milliseconds. As the source material puts it, this is an exercise in ruthless decoupling at a scale that's hard to even imagine.
Okay, so here's our roadmap. We're going to start with the challenge itself. Then look at the core blueprint of the system. From there, we'll trace the two most critical paths, how a link gets created and what happens when you click on it. Then we'll get into the weeds on analytics and resilience. And finally, we'll wrap it all up with the big idea, the core philosophy of decoupling.
All right, first up, let's really get our heads around the unique nature of this hyperscale challenge. It's about more than just big numbers.
So the whole problem really boils down to this one massive imbalance. The source material points out that 100-to-1 read-to-write ratio is pretty standard, but this system is way more extreme. It is overwhelmingly a read-heavy system. Almost everything it does is serving a click. And this ratio, this is the key that unlocks the whole design, because you just can't build a single system that's optimized for both reads and writes when the difference is this huge.
So how do you solve a problem like that? Well, the answer isn't a piece of tech. It's a philosophy. Relentless, absolutely ruthless decoupling.
And this right here, this is the secret sauce. This is the blueprint. Instead of building one giant monolithic service that does everything, the system is intentionally fractured into three completely independent ecosystems. You've got the write service, circled there in red, which only cares about creating new links. Then you have the hyper-optimized read service in blue, which does nothing but handle redirects at insane speeds. And finally, you have the asynchronous analytics pipeline in green. The keyword is isolated. A massive spike in analytics processing can't touch or slow down that critical sub-10 millisecond redirect path. It's brilliant.
Okay, let's dive into that first piece of the puzzle, the write path. We're going to follow a long, clunky URL on its journey to becoming a sleek, short link. So, first things first, you need a unique ID for your short link. Sounds easy, right? Well, not so fast. As you can see, the standard solutions don't really cut it. UUIDs? Way too long, and they are just awful for database indexing performance. What about Twitter's Snowflake algorithm? It's amazing, for sure, but it still spits out an 11-character string. If you just chop that down, you run the risk of two different links getting the same ID. We need something that's short, unique, and database-friendly. And here is the absolutely elegant solution they landed on, a dedicated key generation service, or KGS. It takes a 43-bit integer and encodes it into a clean 7-character base 62 string. The result? It's short, it looks good, and it gives you, wait for it, 3.5 trillion possible unique combinations.
Yeah, that's going to be enough scale for a while.
Okay, so let's trace the full journey here. A user's request comes into the write API. The system instantly grabs one of those pre-generated IDs, runs it through a cipher to obfuscate it, so you can't just guess the next link in the sequence, and then it synchronously saves that mapping to the main spanner database. But this is the crucial part. At the same time, it immediately warms the Redis cache and fires off an event to Kafka. Warming the cache means the very first person to click that brand new link gets that same lightning-fast experience, no cold starts. All right, let's flip over to the other side, the read path. This is where 99.9% of the traffic lives, and it has to be, and I mean has to be, unbelievably fast.
The read path is protected by what the source calls the edge defense funnel, and it's basically a multi-layered fortress. First, requests hit edge workers that can fire back a redirect in under 10 milliseconds right from memory. If it's a cache miss, the next layer is Envoy rate limiting to block noisy bots. After that, a regional Redis cache handles the most popular viral links.
Then, there's a really clever Bloom filter that mathematically proves if a link doesn't exist, dropping those junk requests without ever bothering the database. And only if a request makes it through all of those gates does it finally hit the database. And even then, it's a super fast, stale read, which basically means it grabs data from a local copy that might be a fraction of a second old, all in the name of speed over perfect up to the nanosecond consistency. And how does it feel so fast no matter where you are in the world? Well, it's all thanks to this clever trick called anycast routing. If you're in Europe, you're automatically sent to the European server and database shard. If you're in the US, you go to the US node. It's that simple, and it instantly shaves off over 150 milliseconds of lag from data having to travel across an ocean. So here's the entire read path laid out in a flowchart. The logic is simple. Check the cache, then the Bloom filter, then the database. But look at that rule at the bottom. This is the golden rule of the entire architecture. The read service is explicitly forbidden from ever performing a write operation. That strict, non-negotiable separation is the secret that guarantees its speed and its stability.
Okay, so we've got the main highways covered, the reads and the writes, but what about all the support systems? Collecting data and making sure this thing never, ever falls over. Now this is a brilliant analogy. For analytics, every single click event gets fired into Apache Kafka, and Kafka acts like a giant shock absorber. Just imagine a link goes viral, and suddenly you have millions of clicks flooding in every minute. Kafka doesn't even flinch. It just absorbs that massive, spiky wave of events and lets the back-end analytics processors like Flink and ClickHouse sip on that data at a nice, steady pace. The user-facing redirect service feels nothing.
So how do we know this thing is actually resilient? Well, you try to break it on purpose. This is a chaos engineering matrix. So what if a Redis cache just dies? The system has a fail-open policy. It bypasses the cache, but uses those rate limiters to shield the database. What if an entire data center for Spanner goes offline? No problem. Global Anycast just reroutes all the traffic to the secondary region. For every potential disaster, there's a specific architectural safeguard already in place.
All right, so after all of that incredible technical detail, let's zoom out. What's the one big idea, the main takeaway from this entire system design? And this quote right here just nails the central theme. True hyperscale, the kind we're talking about here, doesn't come from just buying a bigger, faster, more expensive database. It comes from intelligently and relentlessly separating your system's concerns. Isolate the reads, isolate the writes, and isolate the analytics. That is the secret.
Which kind of leaves us with a final thought to chew on. Think about a web service you use every single day. Maybe it's a social media feed or an e-commerce platform. Where are the read-heavy paths? Where are the write-heavy paths? And how could you maybe redesign that service using this exact same philosophy of ruthless decoupling? It's a really powerful way to look at system design.